Hello and welcome to another video. In this video we're going to be doing the last problem of the weekly contest 388 and its maximum strength of k disjoint subarrays. And I will say the description for this problem is kind of not the best, so let's just go over it. So you're given a zero indexed array of integers nums of length n and a positive integer k, and then they give you this whole thing. So basically they tell you that you can pick disjoint subarrays from nums, and the first subarray, the total you're going to get is, so let's say I pick this like 1, 2, 3. Whatever I pick for my first subarray, I'm going to take that sum and then multiply it by the current value of k. So in this case it's 3. So like if I pick 1, 2, 3, I will get 6, and I'll multiply it by 3 and get 18. And then I pick another disjoint subarray. So let's say I pick this, and then now I will subtract the current value of k, and k goes down every time. So k was 3, now it's 2. So I will subtract negative 1 times 2. So basically adding 2 here. And then when k is 1, then you go back to adding, so you can pick another subarray. So let's say I pick this. I will multiply again by the current value of k, and I will add. So here I get 22. And then the next example, because k is 5, you basically have to pick disjoint subarrays that are all separate, so like these, and then you can add those up. And here k is 1, so these are all negative, so you just want to pick negative 1 because that's going to give you the biggest total. So one of the quirks I had with this problem is I thought that the order of the disjoint subarrays didn't matter. So I thought I could pick like this to be my first subarray and this to be my second or something, because they never really stated that the subarrays have to be in order, and so that like made the problem harder. I was kind of confused, and I kind of had to look at like what other people were saying, and other people had the same thing. So it is kind of hard to realize like they didn't really state that the subarrays you have to pick, like the first one has to be before the second one, and so on and so on. So for example, if you want to pick this element 1 or not, if you don't pick it in the first one, you can never pick it again. And so that's a big part of the problem. But once you know that, let's say you do know that. Let's say you do know like, okay, my subarrays have to be in order. So the tricky part here is k and n multiplied together is 10 to the 6th. So you can't just like try a bunch of, you can't just be like, okay, like let's say I have some numbers over here. So let's say I have these like numbers. So 1, 2, 3, negative 1, 2. You can't just be like, okay, well, maybe I'll store like k and n and do some kind of DP, right? I'll store n and k. And then in my function, I'll just try some for loop where I'll try like to put this in my first subarray recurse, put this in my first subarray recurse, put this in my first subarray recurse, right? Because that would basically give you a solution that's n times k times like a for loop, which would be another n. And that would fail. So you need something that's n times k, and then you need your whatever you use. It is a little bit, well, you can think about using DP because you're kind of like trying to pick whether to use something in your subarray or not, and it's recursive and there is like a relationship. So you can't do it that way, but what you can do instead is you can just say, okay, for this element, am I going to use it in my current subarray that I'm looking for? So let's say I'm looking for like my first subarray. Am I going to use it in here or not? If I am, I'll go to the next index and I will update something. And if I'm not, I'll go to the next index and I'll update something. So instead of having a for loop where you're trying like this, 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 and so on, and all these recursions, you're basically asking for each unique element, am I using it in here or am I not? And that brings down your time complexity and it brings up your memory. So that's kind of what we're doing. And the other thing you have to understand is what states do you need? So let's say I want to, like, let's say I'm making my first subarray. So here I need 3. So I'm making my first one. So let's say I have an index like I, it's 0. And then my first subarray I'm making, so let's say maybe j is like the first one. So if I choose to include this, I have a few options, and I didn't realize this as well, and this was kind of tricky. So at first I was like, okay, if I choose to include it, I basically have one of two options. I either include it and I end this subarray, or I include it and I keep going. But that doesn't really end up working, so you actually need 3 options. Because if you end or you keep going, the problem is if you keep going, you actually need to know how many elements are in here. Because let's say I choose to take this element in and then I keep going with this subarray. Now if I'm here, if I choose not to take it, it matters whether my current subarray, how many elements it has. So let's just walk through what I mean. So let's say we choose to take this in our first subarray. So our first subarray will have 1. Then we recurse over here and we say, okay, well, so we're still picking our first subarray. Let's say I choose to keep going with this one. Well, now if I choose not to take 2 and I have something in my current subarray, I actually have to say like, okay, now because I don't choose not to take 2, now I actually have to go to like my next subarray that I'm picking things for. So I would have to say, okay, now J is going to be 2. And now I have to figure out like the next subarray I'm picking things for. But if we go back, if I'm picking for the first one and I choose not to take this, and then I choose not to take this, then I'm still picking for the first subarray. So you have to know a couple things. You have to know index, you have to know what subarray you are on, right, or K or whatever, and you have to know is my subarray. So you don't have to know like is it full or how many items, but does it have items? And this is going to be the least amount of state you can have. So if your subarray has items and you choose to skip something, then you know to go to the next one. If your subarray doesn't have any and you choose to skip something, then you're still on your current one because the subarray has to have at least 1 item. So those are the states you need. And then it'll be fine because does it have items is just like a Boolean, it's true, false. So that's just like, that adds 2 things. And so your states can be n times k times 2, which is 10 to the 6 times 2, which should be fine. And so what I will say for this one, also the time constraints are really tight. So I did this in memorization and I got a memory limit exceeded. But essentially, let's kind of walk through now what like kind of a little bit what it's going to look like for at least a couple states. So let's go through this one right here. And let's maybe draw like a subtree of it. So in the beginning, let's just do that. So basically here's our tree. So our I is 0. The way I had it, I think was, I think what I had was like, I pick which subarray I'm picking. So let's say, so I made it equal to k to start off. And then when it's 0, that means I have like nothing left. So the second variable is like how many subarrays I have left to fill. So the second variable will be 3. And then the third variable is, does my current subarray have items? So right now it's false. So let's see the options we have here. So option A, take the 1 and go to the next subarray. So that means we'll get a value of 1 and it'll be positive, and then we go to the next subarray. So what will this be? So this will be 1. Now we have 2 subarrays left to fill, and we're filling like a new subarray now because we filled up this one. So this next one is empty. So we'll have a false. Option 2, take the 1 and still keep filling up the current subarray. So here, that will be 1. Now we'll still have this 3 because we're still filling up this one. And now this will be true as in this has items. And then option 3 is just don't take it at all. So that would be 1 and 3 still, and false because we don't have any items. So let's get rid of this and move some stuff down so we have a little bit more space to work with. So let's move this over here. So let's do like maybe one more of each of these. Okay, so over here, once again, we have 3 options. So in this state means we're on index 1. We're filling out the second subarray, or we have 2 subarrays left to fill, and our current subarray doesn't have items, false. So option A, we can take the item and we can continue filling out the current subarray we're on. So what's that going to look like? That's going to look like 2. If we take the item and we keep filling out the current subarray, or actually, let's keep with this kind of thing. So we take the item and then we go to the next subarray. So the next subarray would be, we have 1 left and it's empty. And if we take the item, we're at index 1, so this is going to be a value of 2. Now option B is we take the item, but we stay on the current subarray we're on. So that's going to be 2, 2, true, with a value of 2, right? Because this second subarray now has this item, and we're going to stay with this one. And option 3 is don't take it at all. So we'll try to have some space here. So don't take it at all. So it's going to be 2, 2, and false. Okay, so let's just fill out like maybe this one as well. We don't need to do all of them. So we'll fill out this, and this is basically the same kind of thing all the way down. So here we're going to choose to take the item and go to the next subarray. So if we take the item, we are on index 1, so this is going to be a value of 2. And if we take the item and we go to the next subarray, so it's going to be 2, 2. And if we go to the next subarray, so it's as soon as every time we go to the next subarray, it's going to be empty. So as in, does it have an item? We'll say false. Now the middle one, take the item and stay on the same subarray. So 2. And here it's going to be 2, stay on the same subarray, so we'll stay on subarray number 3, and now it has an item. And option 3, don't take it at all. So 2, 3, false. So you can kind of see it's going to stay with this pattern basically, and you do this, and then your base cases are so when you have no more subarrays to fill, you just return 0. Right, so we can write that down. So no more subarrays, return 0. Now there is a case you can do to return early. So let's say you're on some index and you still need a bunch more subarrays. Like let's say here, I'm on this index. So based on the index and the length of your actual array, you know how many more items you have left. So here you have 5. So if you need to fill out, if like the number of subarrays you need to fill out, let's call that k, is greater than the length you have left, then obviously like you can't do that, right? So if you need to fill like 6 more subarrays, but you only have 5 more items, you can just return. And what do we want to return in this case? We can just return negative infinity, right? So we want to make sure this never gets used. So no more subarrays, we'll return 0, and not enough items, we'll return negative infinity. And also out of bounds, well, I guess that will cover the not enough items, right? So this out of bounds will actually cover the not enough items, because here we'd be out of bounds and k wouldn't be 0. So basically, if we can't fill out the rest of our subarrays, we return negative infinity. Otherwise, we just have our 3 conditions. So we either take the item and stay on their current subarray, we take the item and go to the next subarray, or we just skip the item. And like I said, you have to know where you're at, because it does change like the recursive state. So let's take a look at that. Let's see here. Here it is. So we have our n, and then we have like a basic DP function. So I is the index we're at, j is how many subarrays we have left, and useNum is does our subarray contain a number. So if we have no more subarrays to fill out, let's return 0. I think this is actually not needed. I think this case will always cover it. Let's just double check. Yeah, I think it does. So as you can see though, when I run this, we actually get a TLE, so the time constraints, or I guess this was a memory failure, which is surprising, because like from the constraints it should be fine, but either way it didn't work. So yeah, so this is the case where we don't have enough items. Then we just figure out like what's the value of our number. So the value of our number is just based on like what subarray we're on, and we figure out like is it positive or negative, and the way to do that. So let's say k is like 3, and we are on subarray number 1 or something or whatever, some number. We just do k minus the current subarray we're on, and if that number is even, then it's positive, and if it's odd, then it's negative. So pretty straightforward to figure that part out. So you just make your number negative if you need to. Now you make your result. And so your result is using the number. That's 2 of your cases. So if you use the number, you just figure out, okay, I either stay on the subarray or go to the next one. So this is going to the next one. So if you go to the next one, you have 1 less subarray to fill, and your current subarray will be empty now because you're going to the next one. If you stay on the current one, you still have the same number of subarrays to fill, and now your subarray has an item. And then this case is going to be the 2 different things. So if your subarray has an item and you choose, this is the 2 cases where you choose not to take the item. If your subarray has an item and you choose not to take an item, then you're basically done with this subarray and you have to go to the next one because they have to be contiguous. So your next subarray will just be empty. And if your subarray doesn't have any items, then you just go to the next index and you're still on your same subarray because the subarray has to have at least one item. So that's why you need to have this variable to know if your subarray has at least one item. So if you choose not to take something, you need to know, do I go to the next one or do I stay on this one? Then you return it and you just start off by calling it on index 0 with k with false. So yeah, if I run this, I got a memory error. So I was like, and this is a good exercise for you. So look at the recursive states and see, okay, we got a memory error. We need to free up some memory. Obviously, bottom-up DP is more efficient, but also notice that all of these recursive states, I is I plus 1, so we can actually get rid of this I dimension. So we can have space be k times 2, which is just k. And then our time will be the same, but our space will be k, so surely that's going to easily pass, as long as our time was fast enough. So here is me making a bottom-up. Took a little while, but... So essentially, for every single number in the range of 0 to k, I just made 2 numbers. So one of these represents having a subarray with an item, and the other one represents having a subarray without an item. So our base case is we are out of bounds, and so if we are out of bounds, the only valid state is when k is 0. So when k is 0, I just made both of these things 0, right? Holding an item or not. Then we just go backwards in the index. So we start at the second to last index, and we go back through the array. We make this new DP. This is just a standard space optimized bottom up. So you make a new DP, and then the same thing, whatever index you're on, if you don't need any more subarrays, that is always going to be your base case. So we just make that 0, and then we go through every single number in the range of so I made it like this, and then I broke. So basically, I tried to fill up every single number of k from 1 to k, and if we don't have enough to fill, then we can just break out of this loop, right? So whatever index we're on. So technically, you don't need to. You can make this a little bit more efficient. Like here, I made an array of k items, but really, if you think about it, like let's say you are on this index, you don't need to make an array of k items. If k is like 10, you only need like 3 or 4. Because any more than that will never work. So if you want to make it a little bit more efficient, you can do that. I just did it like this. Yeah, so if we don't have enough items to break, same thing, calculate our value that we're getting. If we're on an odd index, then we need to make it negative. And then here is the result of using the value. So if you use the value, it's going to be, you either go to the next subarray, which is dp of j minus 1, right? You have one less subarray, and 1 in this case means, I wrote this down so I wouldn't forget. So 1 means we're not holding an item, like this index 1, I have to figure out which one is which. So this index represents we're not holding an item, this index represents we are holding an item. You can use a dictionary if you want with like true and false if that makes things easier. Yeah, so if we are holding an item and we go to the next subarray, then we're not going to be holding an item, so 1 is not holding an item. And if we are holding an item and we choose to stay on the same one, then we'll have the same number of subarrays and we are holding an item. And then we have the 2 cases of when we skip the item. So if we are holding an item and we skip it, then we have 1 less subarray to fill now, and then we're not holding an item. If we're not holding an item and we skip it, then we're still on the same subarray because we need to have at least 1 element in here. And then at the very end, you just make your DP new DP. Yeah, if you've been seeing like all my space optimized bottom-up problems, it's basically the same template in all of these. So it just takes a little bit while to code because this is like a 3D one. So you can use a dictionary. Dictionary would probably make it a little bit easier. And then yeah, so your base case is return DP. So if you do this backwards, your DP will be the DP of all the Ks at index 0. And the one you want is the K that was passed in when you are not holding an item, right? Because in the beginning you don't hold anything, so that's 1. So you want to return DP of K1, and yeah, let's run this. And like I said, I tried to optimize it. I think some solutions were a little bit faster, but this was good enough to pass. And it's a pretty rare case where DP memoization doesn't pass. So I think the constraints on this problem are kind of bad. The description's kind of bad, where you didn't really tell you that like your subarrays have to be in order. So I think this problem overall is just like not the best. But once you do get what you need to do, this is definitely a good practice to do space optimized bottom up. It's basically as hard as it gets because this is like a 3D one. I mean, I guess the third dimension is a little easy. It's only like true or false, but still. Yeah, so we can talk about time and space here. So time is going to be n times k times 2, technically, and space is going to be O of k. Because we got rid of the n dimension, because like I said, common thing when you write memoization and you notice that all your recursive states have like I plus 1 or whatever, one of your states is like I plus 1, I minus 1, and so on. You can get rid of that. So we got rid of that state. So our DP now is only space k times 2. But yeah, so that's going to be all for this one. Hopefully you liked it. If you have any questions, as always, write in the comments or anything. And if this was useful for you, then please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.